ahead and begin today's discussion dealing with another one of these little shortcut rules that we can come up with and use when trying to find derivatives. Last time we looked at an example of where we had x raised to some power. We had what was called the power rule. And the power rule said that if you have a function, and it can vary a little bit from this, but if you have somewhere in your function x raised to the nth power, that you can find the derivative very quickly by bringing that n out front and then decreasing the power by 1. Okay, and this is the rule that we spent some time with last time. And the nice thing about it was it worked for nice integers, it worked for fractions, it worked for decimals, it worked for pi. I mean, it works for practically anything. Okay? So this was a good rule, a nice little shortcut to save us from having to go through so much work when we're calculating derivatives. Now, today we want to look at what if we have two functions that are multiplied together. You know, what if we have a product of two functions multiplied together? And the name we will give this is called the product rule. And I want to look at a specific example here. Okay? What if we have a function f of x, which is defined by 3x to the third, and then we have another function g of x, which is defined as 4x to the fourth plus 1. And our goal is we're going to multiply these together and find a derivative. Okay? So f of x times g of x. Okay, I'll just be rewriting it at this stage. All right, and so this is our function. Now, intuitively, or at least what seems like might make some sense, is that if we have two functions multiplied together, okay, we might just be able to take the derivative of the first piece, the f of x part, and then multiply by the derivative of the second piece, the g of x part. Okay, and so let's try that. Let's just see if it works. Okay, so what if I just take the derivative of the first part, and I take the derivative of the second part? Let's see what answer we come up with. Okay? Well, just reviewing from the other day, what is a derivative of 3x to the third? 20. Okay? 9x squared, right? The 3 comes down front. 3 times 3 is 9. We decrease the power by 1. Okay? What is the derivative of 4x to the fourth? 16x cubed. And the derivative of 1 is 0. Okay, 1 is a straight horizontal line, so it does not have a slope. It has a slope of 0. Okay, and so this answer, if I was to go through and clean this up, let's see, 16 times 9, I believe, is 144, and x squared times x cubed is x to the fifth. And so right now, we're not sure about this, so I'll put a little question mark above it here. We think that the derivative might be 144 times x to the fifth. Okay, now, the way that we can be absolutely sure if this is the correct answer is for us to go back up here to the original product of these two functions. Let's actually go through and distribute this, 3x to the third. Let's actually multiply it out and in essence get rid of the product. Okay? So here's what I mean. I'm going to take this up right up to here. Okay? If I was to distribute this out, I would get 12x to the seventh. And if I was to distribute 2 times 1, of course, that doesn't change anything. So plus 3x to the third. Notice my goal with this is to eliminate the product because now we know how to take derivative of two polynomials added together. And our question is, when we take this derivative, is that answer going to match up with this answer down here? Okay? And right away, you might already be able to tell that that is going to be no. They do not match up. So our instinct or our intuition told us we might just be able to take the derivative of the first times the derivative of the second and get the answer. But we have now found out that is not the correct formula for taking the derivative of a product. Okay? Now, let's go ahead and actually find this derivative. So let's find out what the correct answer should be, and then we will talk about what the rule really is for products. Okay? All right, so the derivative up here, this would be 84x to the sixth. And then this would be 9x squared. Okay? So it looks like the correct answer for our derivative should be in a form that looks like this, as opposed to just taking two products and multiplying together. Now, I want to go ahead and put down the definition for the product rule. It's actually seems kind of long, but it's really not a bad definition here. Okay, here's the definition for product rule. All right. If we've got some function f of x times another function g of x, and we want to find its derivative, okay? The derivative equals, we're going to take the first part of the function, the first part of the product, and just leave it, f of x, just stays there. Now we're going to multiply that by g prime of x. Okay? So we take the first piece times the derivative of the second piece, and then plus we do the exact opposite. We take the second piece times the derivative of the first piece. And again, if this was a course dealing where all of you were math majors, we would go through and would have developed this and proven why this works, but I don't think that's the focus of this course. We're just going to assume that, yeah, that's the correct rule, and we're just going to learn how to use it and apply it. Okay? So this is the definition of derivative when we deal with a product. So we had part of the rule correct. You know, we had the f prime and the g prime as part of the answer, but we didn't realize that we had to leave the original functions in there as well. Okay? Now, let's go ahead and let's take the derivative, back to this same example. Let's go ahead and take the derivative correctly using the product rule and show that it matches up with the correct answer from up here. Okay, just to verify that, convince you that this really works. Okay, f of x is just 3x to the third. So I rewrite the first part of my product. I'm going to multiply that by the derivative of the other part. And what's the derivative of the second part? What's the derivative of this? 16x cubed. Okay, so this times this. All right, plus. Okay, what is g of x? That's our 4x to the fourth plus 1. And then we need to multiply that by the f prime of x piece. And what's f prime of x? What's the derivative of f? 9x squared. Okay, now we just need to go through and clean this up a little bit. We'll probably have to put a couple of like terms together to try to get it to match up with this term up here. Okay, all right, these two together can make a 48x to the sixth. And if I distribute the 9x squared through the parentheses here, looks like I'll get 36x to the sixth and 9x squared. Okay, I've got a couple of x to the sixth terms. If I was to add these two together, does that give me 84? X to the sixth. And the answer is yes. Okay, so we did match up. 9x squared. Okay, and so we verified, yes, this product rule does work. Okay, and the only thing that you'll have to do now is you'll just have to remember what this rule is. It's really not a hard rule. You just take one part times the derivative of the other part, and then you flip the process around. There's an addition sign in the middle, so it really doesn't matter what order you go in. Okay, so it works out either way. Okay, so this is a nice little rule that we can use to take the derivative of products. Now, one question that may be coming up is, why would we want to have a complicated rule for taking derivative of products where it looks like it took more work to do this than it did for us to just actually distribute through and get the answer the old-fashioned way, the way that we talked about last time? Why would we want to have a product rule? Okay? Well, the reason is because this example that I chose is rather basic. Okay? Yes, in this case, it was faster to distribute and just take the derivatives in this form. But as we progress through the course, we won't have functions that are this easy or that are this nice. Okay? And so when we get to those types of equations, we will find out that it is easier to use the product rule than it is to go through and actually FOIL things out. Okay? In fact, we'll get to some places where we won't be able to FOIL things out. We might have a natural log function out here. And natural log times something in here may not simplify very nicely. So we'll fall back on the product rule. Okay? All right. Let's look at some more examples of product rule here, just to get a little more practice with it here. What if we've got y equals 3x squared plus 1 as the first, 3x squared plus 2 as the first part, and the second part 2x minus 1. Okay? And our goal is just for right now, calculate dy dx. Okay? Calculate the derivative of this function. Okay? First thing we recognize, this is a product. We have one function times another function, so we either need to do one of two things. Either multiply the function out, distribute through the parentheses, and then take the derivative, or the other option is use the product rule. Well, let's go ahead and practice the product rule since that's our focus here today. All right, the product rule says take one of the terms, either one, and just write it as it is. Okay, I'll just take the first term and rewrite it as it is. I now need to multiply by what? The derivative of the other term, right. So I wrote the first one as it was. What's the derivative of the second term? 2, right. The derivative of 2x is 2. The derivative of negative 1 is 0. Right, so the derivative here is 2. Okay. Then plus, I do things in the opposite order. I now rewrite the second term, or the second part of the product, as it is, and multiply by the derivative of the first piece. And what is the derivative of the first part? 6x, right. Okay. And then my last step is to now go through and try to put all the like terms together. And the reason we want to put like terms together is that as we move on here, we will be getting into problems where they will be asking us, where is the derivative equal to 0? And whenever we get to those types of problems, it'll be much easier for us to solve those types of equations if we put all the like terms together. Okay? So let's go ahead and do that for right now. Let's go ahead and clean this up. Okay? Let's see. If I take this times this, and if I take this times this, and just put them all together, how many x squared terms do we have? Kind of skipping a step here in the middle, but how many x squared terms total? Okay, 2 terms, and how many, like here we've got 6 of them, and here we've got 12 of them, so that's a total of 18x squared, right? Okay, so we got 18x squared out of this. Okay, let's see, if I multiply this times this, I get negative 6x, and that's the only x, or the only linear term. And if I multiply this times this, I get a plus 4. Okay? And so this is what I mean by cleaning it up. Go through, distribute, put all the like terms together. Now, if this was a question that said go ahead and set the derivative equal to 0, we can now have a quadratic equation set equal to 0. And we talked earlier this semester about how we solve those types of equations. We're not going to do that right now. Okay? But this is the actual derivative, dy dx, okay, for the product that we began with up here at the top. Okay, questions with that? All right. Another example, which on the surface does not look like a product rule, but it actually can be. What if I give you y equals 2x minus 5 quantity squared? Okay. How can I rewrite this so that I could use the product rule? Yeah, exactly. Okay. Squaring a function means I'm just taking the function and multiplying it by itself. Okay? And so we need to do this. We need to rewrite this as 2x minus 5 times 2x minus 5. Now, some of you may be questioning, okay, why couldn't we just take the 2 and bring it out front and have all this raised to the first power and that be our derivative? Well, we haven't talked about this situation yet. This is different than yesterday. Because yesterday, what type of numbers were we squaring? Well, we just had x's in here, didn't we? X to some power. We know how to take that derivative. Do we know how to take a function squared's derivative? And the answer is no. That will be coming up next time. Okay, so be a little careful with this. We do need to split it apart as a product. Okay, now let's go ahead and run through this. dy dx. Okay, so kind of talk me through this here. What's the first piece? Yep, 2x minus 5 times what? Times the derivative of the second part. Derivative of this one is 2. Okay, plus 2x minus 5 again. Okay. This 2x minus 5 was probably this one, and this 2x minus 5 is the other one. And then I multiply by what? The derivative of the first piece, which happens to also be 2, right? Okay. The nice thing about this, you do get the same numbers because you've got the same factors up here at the top. All right, if we clean this up here, okay, if we combine all those x terms together, how many do we have? Here we've got 4x, there we've got another 4x, so it looks like we have a total of 8x when this all goes together. And if we put these terms together, we end up with what? Minus 20. So the derivative of this function, 2x minus 5 quantity squared, is 8x minus 20. Okay? Now, I want to go ahead and do this example. I want to set it equal to 0. And I want to solve for x because I want to discuss with you what this means. Okay? First of all, let's go ahead and solve this. Solving it's very simple. We just need to add 20 to both sides and then divide off the 8. Okay? So 20 divided by 8 is our value for x. Now, what's happening at 20 over 8 on this particular function, 2x minus 5 squared? What does it mean if we're going to take the derivative and set it equal to 0? What's another word for derivative? Slope. What does it mean if a function has a slope of 0? Okay, it means one of two things. Where do graphs have slopes of 0? Okay, well, either they can have a slope of 0 at a peak, this would be a slope of 0, or they can have a slope of 0 at a valley. This has a slope of 0. So what we have found here is we have found the only location on this function that has a peak or a valley. There's only one peak or valley. We don't know which one it is yet. Okay? But this is the only location where there is a peak or valley on this particular function. Okay? Right? So that's one thing that they will begin to have you do here is start to evaluate derivatives equal to 0 because that helps us determine where these types of locations are at. All right, any questions with this product rule? All right, very good. The next thing we want to look at here today is what if instead of a product of two functions, what if we have a quotient? So what if we have one polynomial or one function divided by another function? How do we take the derivative when division is involved? Okay. Well, let me start out with the example here. Let's say that our function f of x is defined this way. N of x divided by d of x. And I'm picking n and d to stand for numerator and denominator. Okay, this will help us as we start going through the actual formula to remind ourselves where the numerator and denominator were. Okay? All right. I'm actually going to do a little bit of theory with you on this one because it's not a bad little proof if we want to figure out what the quotient rule really is. Okay? Here's what I'm going to have us do. This is our original function, and our goal is to find f prime of x. We want the derivative. Okay, so here's how we're going to do this. I'm going to multiply both sides by d of x. Okay, so I've got d of x times f of x equals n of x. And my reason for doing this is now, instead of a quotient rule, what type of problem have I turned this into? A product rule, right? And we just learned how to do the product rule. Okay, and again, this is a proof, this is theory, so I won't ask this on an exam, but it's kind of a neat little way to show what the quotient rule is. Let's turn our quotients into products and then just use the rule we already know. Okay? All right, so now what we do is we want to go through and take the derivative of both sides. Okay? How do we take the derivative of a product? Well, I'm going to write the first term as it is and multiply by what? Somebody said it. The derivative of the second term, right? We write the first one as it is and we multiply by the derivative of the second piece. Okay, so d times f prime of x. Okay, plus, what's the second part of the product rule? The opposite. I'm going to write the f of x as it is and multiply by what? D prime of x, the derivative of the other piece, right? Okay. So this is the derivative of the left side according to the product rule. Okay. What's the derivative of the right side? Well, that's just n prime of x. Okay. We don't have to do anything fancy with it. We just write it, that's its derivative. Okay. Now we want to go through and try to solve this equation. We want to solve this for f prime of x because that was the initial goal. So let's find the derivative for function f. Okay? The only thing else that I'm going to do is I'm going to replace this f of x, I'm going to replace it with n divided by d. Right? So let's go ahead and do that first. So this times f prime of x plus, then we make our substitution, n of x over d of x times d prime of x equals n prime of x. Okay, so we're just making a substitution. Our goal with making the substitution, I really don't want any f of x's in my final answer. I want everything in terms of d's and n's. Okay? All right, if I want to solve this equation for f prime of x, okay, notice I have something plus something equals something else. What will I need to do to try to isolate this term? Okay, couple of things I can do. One of them is I can try to go through and get rid of this fraction first. Okay, and then in fact, let's go ahead and do that one first. Okay, so I'm going to multiply each term, this one, and this one. I'm going to multiply them all by d of x just to get rid of the fraction. Okay, d of x times another d of x, that's d squared of x. That's something times something is just squared. Okay, times f prime of x. Okay, the middle term now looks similar except it's missing that denominator. We multiplied it through. And on the right side, we've got n prime of x times that d of x. Okay, now what would I do if I want to isolate this term? You know, just off to the side, what if I had 3 plus x equals 7? How do I isolate the term that I want? I subtract the 3 over. I subtract that piece over to the other side. Okay, so what piece do I want to subtract? Do I want to subtract the first one or the second one? Second one, right. I want to subtract this term over to the right side because I want to keep the f prime by itself. Okay, so d squared times f prime equals n prime of x times d of x minus n of x times d prime of x. Okay, it's kind of confusing because you got n's and d's and primes, but okay, once we're all finished, it will make sense. Now, what's the last thing I need to do to isolate this f prime of x? How do I get rid of this d squared? Divide, correct. Because if I've got multiplication right now, I need to divide that term off to the other side. Okay, I'm not going to rewrite everything. I'll just write it all divided by d squared of x. Okay, and this rule that we have come up with now, this one right here, this is called the quotient rule. And you can see that it's a little messier than the product rule. But if we look at it a little closer, it is a rule that we can memorize as well. It's really not too bad. Look at what we've got up in the numerator. We've got the numerator's derivative times the denominator. And here we've got the denominator's derivative times the numerator. Isn't that kind of what we had up in the product rule? You take one of them times the derivative of the other one and then vice versa. The only thing that's a little harder about this one is we have a subtraction sign in the middle. And the subtraction sign makes a huge difference. Okay? Because often, again, just off to the side, is 5 minus 4, is that the same as 4 minus 5? No. So we have to be really careful on the order on this one. On the product rule, we didn't have to worry because 5 plus 4 is the same as 4 plus 5. Those are the same. But here, we don't have that luxury. So we've got to be really careful. Make sure we take the derivative of the numerator first, and then the derivative of the denominator comes over here on the second component. Okay? And then the last thing is, there's a little bit more of part of the process. All we've got to do in the denominator is we've just got to square the denominator, and we'll have our answer. Okay? All right, so here's the theory. Now let's go and do an example or two, and then I think it'll make more sense. Okay, first example we will do, let's just take two linear terms divided by each other. 7x plus 1 and 3x plus 8. And we want to find the derivative of this function. All right. What did the rule for quotients tell us to do? What do we start with? Okay, we start with n prime of x. So we take the derivative of the numerator, which is what? 7 times what? Times the d of x, the denominator, 3x plus 8. So I take the derivative of the numerator times the denominator. Okay, then I've got the subtraction sign. Now what do? Well, I switch the order. I switch the process. Now I'm going to multiply by the derivative of the denominator, which is 3 times the numerator, 7x plus 1. Okay? Divided by the denominator squared. And usually all we do to square the denominator is just rewrite it denominator squared, just like this. It is very rare when we want to actually go through and FOIL this out. Okay? And as we get to the examples later, you'll see why we don't really need to do that. Okay? The last thing that we do want to do, though, up in the numerator, we do want to clean up the numerator, simplify it. Don't worry about doing anything in the denominator, but do clean up the numerator. Okay? All right, if we go through and look at all the x terms, what happens to those x terms? They cancel out, don't they? Here's 21x. Here's minus 21x. So the x terms all go away. All right, what do we have here? We've got 56 minus 3. So looks like the numerator cleans up all the way down to 53. Okay? All right, and so this is the derivative of the quotient that we started with up here. Now again, just to give you a little background on this, why do we want to simplify the numerator and not simplify the denominator? Well, it's the same type of questions that we will be working with on the product rules. There will be a lot of times where we want to set this derivative equal to 0. And if you remember back way to the first day of class, we talked about this. If I have a quotient that needs to equal 0, what type of fractions give me 0 for an answer? Is this the one that equals 0, or is this the one that equals 0? Well, it's the second one, isn't it? Okay, so do I really care what the denominator is? If I'm trying to get this to be 0, do I really care what happens down here? No, because if this is a 7, I still get 0. If this is a 5, I still get 0. I don't care what the denominator is. As long as my numerator turns into 0, I can get an answer of 0. Now, what about this particular example we've got right here? Can this numerator ever equal 0? Can 53 ever equal 0? No. Okay? What does that mean for us? If the derivative or the slope can never equal 0, what does that mean about peaks and valleys on our graph? We don't have any peaks or valleys. If the numerator, or in this case the derivative, can never be 0, it just means that our graph will either be increasing the whole time or else it'll be decreasing the whole time because there's no peaks or valleys anywhere in the graph. Okay, and this can be very helpful for us, especially when we start getting into the applications. This will tell us that certain answers or certain possibilities for answers can be eliminated. Okay? All right, so there's the example, one example of a quotient rule. Okay, let's do one more example of this. Okay, what if we've got y equals 5x plus 6 up in the numerator, and in the denominator we've got a square root of x. And our goal is to find the derivative of this quotient, dy dx. All right, where do we start? Start with the derivative of the numerator. Right, derivative of the numerator is what? 5. Times, I multiply the derivative of one times the actual function on the other one. So 5 times square root of x. Okay, minus, now what? Kind of switch the order of our derivatives, right? Okay, so I took the top times the derivative, I took the derivative of the top times the bottom. Now I need to take the derivative of the bottom times the top. Okay, so what's the derivative of the square root of x? Well, let me just remind you, how do we want to think about this? X to the what? 1/2. Think about it as x to the 1/2. And what's the derivative of x to the 1/2? 1/2 x to the minus 1/2. Okay, we need to take away a full unit from 1/2, so that's negative 1/2. Okay, so here's the derivative of the bottom, and now we need to multiply that times the top. So 5x plus 6. Okay, all divided by, what is the bottom squared? It's just x. Yeah, if I take the square root and then I square it, well then it just goes away and it's x. Okay, and then again, the last thing to do, try to clean up the numerator the best we can. And this will clean up fairly well. Okay, all right, not much I can do with this one for right now. What do I get when I multiply this times this? First of all, 5 times 1/2 is just 5 over 2. What's x times x to the minus 1/2? If I put that together, what is that? Okay, don't let the fractions scare you. Just off to the side here, what if I told you what's x squared times x cubed? You'd tell me what? X to the 5th. Okay, so what did you do? Well, you just added them together. Okay, so what if we do that over here? What if we add 1 and then a negative 1/2? Positive 1/2, isn't it? Okay, so we're doing the same thing, except we just had a fraction this time. Okay, all right. Then I multiply through, and the second one is just times 6, so all that will do is affect this first number. It'll turn it into a 3, and then x to the minus 1/2, all divided by x. Okay? Now, the reason we wanted to go through and multiply this, these two terms now they're similar, so I can add those two together. Okay, I probably shouldn't have drawn an, I don't want this to look like distributive property. Okay, these two have the same x to the 1/2, so we join them together. 5 minus 5/2 would be 2.5. X to the 1/2 minus 3 x to the minus 1/2, all divided by x. Okay, and this is your derivative of our original function here. Gets a little bit messier when you start having square roots or fraction powers in there, but the process is still the same. Okay. All right, questions with this? All right, so we've got a product rule and we've got a quotient rule. Okay, now I want to look at some specific applications of this. I want to look at some specific examples here. I'm going to put them up on the overhead so you can see which ones we are looking at here. Okay, I'm going to look at this example right here. Okay, this average cost question. Okay, it says the total cost in hundreds of dollars to produce X units of perfume is given by this equation, 3x plus 2 over x minus 4. It says find the average cost for each production level. Okay. Now, this is a new definition for us, average cost, although it shouldn't be a really difficult one if we just think about it here for a little bit. Okay. If I look at question A, if I plug in 10 into this function, what will that be telling me? What is C of x in this problem? It is the cost and it is the total cost, isn't it? Okay? So if I plug in 10, that will tell me how much it costs to produce 10 units. Okay? But the question doesn't say what's the total cost. The question says find the average cost. In other words, how much per item. Okay? So what will I need to do once I plug in 10 into this equation? I need to divide by 10. I just need to split that total cost up among the 10 units. Exactly. So whenever we want to find an average cost, and I want to give the definition up here on the board because it's a new symbol. Okay? If we ever want to find something called average cost, okay, they will put a bar above the C. That stands for average. Okay? So if we ever want to find the average cost of a function, we just need to take the total cost and divide it by how many ever items there are. C of x divided by x. Right? So this is our rule. If you ever see this in the book with a bar above it, it's referring to average. Okay? All right, so now let's go ahead and do part A. Part A wanted to know what was the average cost for 10 units. Okay? So C bar of 10, in other words. Okay? All right, if we go back and plug 10 into that equation, what's my numerator? 32, denominator is 14, so 32 divided by 14. That's what I get up on the top. And then x in this problem is what? X is the number of items, so x is 10. So I'm going to take whatever 32 over 14 is, and I'm going to divide that by 10, and whatever answer I get, somebody punch that in, please, so I can talk about a label. How much? 0.23. Okay. So the answer is 0.23. Now, what is 0.23? Well, it's an average cost, but here's the thing that I want us to look at. This 0.23 comes from division up here. So if we look at the label for this, divided by the label for this, that's our label down here. So my first question, what do we probably assume that this is in right here? Okay, total cost is usually in dollars probably, okay? So the label for the numerator is dollars. The label for the denominator, x, is what? Okay, units, right. This is just the number of units of perfume we're producing here, right? Okay, so what is the label for 0.23? It's dollars per unit. Okay, is the label for this. Okay, so the average cost is $0.23 per unit. Now, I have to be a little bit careful here because what did it say about the total cost in our problem? It said it was in hundreds of dollars, so what do I need to do with this decimal point? Need to move it 2 places to the right, yeah. Okay. Since the question said hundreds of dollars, we move this over, and now we see this answer makes a little more sense. It is now $23 per unit instead of 23 cents per unit. Okay. So that's the average cost to make 10 items. Okay. All right. Part B is very similar. We would just plug in 20 instead of 10, so I'm going to skip that one. Okay. Part C wants to know what would this be if we just plug in any number. What if we just plug in x? Okay. Well, I'm going to go ahead and write this down on the board because we will need it then for part D. It's not a difficult process because we don't have to plug in any numbers. All I need to do is rewrite the function c of x divided by x. So I take this whole thing and I divide it by x. And this is my average cost function for any number x. So now I can just take x and sub it in here, and I'll get my average cost for any number. Okay, the reason I want to do that is now look at what D says. Find the marginal average cost function. Okay, it's still talking about average cost function, but now they've thrown one more word in there. They've thrown in the word marginal. What does marginal mean? We talked about it way back at the beginning of the semester. If you ever see the word marginal, that is another word for slope. Slope is another word for what? Derivative. So what they want us to do is they want us to find the derivative of this average cost function. So we're going to find the derivative of this. Okay, now, this is going to take a little bit of work to get it set up initially, but after that it won't be too bad. Okay, so I'm looking for c bar prime of x. Okay, kind of goofy with notation because we got bars and primes. Okay, but this is the function that we're looking at. Now, before I do that though, we should try to simplify or clean this up here a little bit. Okay, where does this x belong if I move it up in here to the numerator? Does it go up here in the numerator or does it go in this denominator? Okay, and the answer to that question is, if I want to get rid of this x on the bottom, I would have to multiply by 1 over x. But if I'm going to multiply by 1 over x on the bottom, I've also got to multiply by 1 over x on the top. And so now the bottom piece disappears, and where did that x end up? It ends up in the denominator, doesn't it? Okay? So if we were to rewrite this, okay, I'm going to take away the prime for just a minute here. We're not doing the derivative yet. If we just rewrite this, we've got 3x plus 2, and here we've got x plus 4 times x. Now, at this stage, I'm going to make a recommendation. Okay, you're going to save yourself a lot of grief if you do this. Okay? Notice we have a quotient, so we'll have to use quotient rule. But notice within the quotient, what do we have down here? We have a product, don't we? So we are actually going to have to do the quotient rule, and then within that, we would have to do a product rule. And that's pretty messy. We want to try to avoid that if we can. Okay? So my recommendation will be, let's FOIL out this denominator, and by doing so, we will eliminate that product out of the denominator. Okay? And that will make our life a lot easier when we're trying to take this derivative. Here's what I mean. Okay? Numerator stays the same. If I FOIL that x through the parentheses, I get x squared plus 4x. Do I have a product on the bottom anymore? No. So now I don't have to mess with a product rule in here. I can just strictly focus on doing a quotient rule. And if you can ever do this, if you can ever clean problems up to eliminate a rule, that's a very good thing to do. It'll save you a lot of grief. Okay? All right, now let's take the derivative of this. How do we take the derivative of a quotient? Start with the derivative of the numerator, which is 3 times the denominator. Okay, the quotient one has a minus sign in it. The derivative of the bottom is okay, so go ahead. Yeah, you're right. Okay, close. The 2 comes out, 2x plus 4. Right, exactly. Okay, times the numerator, which is 3x plus 2, divided by, what do we do with the denominator down here? Square it. So x squared plus 4x, quantity squared. Okay. Again, the only thing that we really need to simplify, try to clean up the numerator a little bit. Try to put all the like terms together. This will make it a lot easier when we have to set these to 0 in a little while. Okay. And we can do this in a, try to do, don't have to write so many steps here. Okay, I got 3x squareds over here. I've got how many x squareds over here? -6, so it looks like -3x squareds all together. Okay. Over here, I've got 12x terms over here. Well, what about this one right here? That's -12x, right? So that canceled off these 12x over here. But do I have any other x terms over here? Yeah, first times last. Okay, so what do I end up with? Looks like -4x. Okay. And again, if you need to write out more of these steps, that's okay. I mean, there's nothing wrong with that. Okay. So we've taken care of all the multiplication on the first one. We've done 3 of the 4 parts of FOIL over here. The only thing left on FOIL we haven't done is last times last. So it looks like that'll be a -8. Be really careful when you're simplifying these. This negative sign goes through the whole FOIL process. So make sure you don't lose that negative sign. And then the bottom we just leave. Quantity squared. Okay, this is the marginal average cost function right down here. Okay. All right, very good. Let's try one more example. Okay, let's just slide across here to a life science question. This will probably be actually a little easier even. It says when a certain drug is injected into a muscle, the muscle responds by contracting. The amount of contraction in millimeters is related to the concentration of the drug. That makes sense. The more drug you put in, the more that the muscle will probably contract. Okay? And it's related by this equation. S of x equals x divided by m plus nx. Oh, okay, that's just a comma over there. Okay, I thought that was a power. Yeah. All right, so just x over m plus nx. M and n are constants that we will plug in. Notice in part B we'll get the numbers for them. Part A says find the derivative. Find s prime of x. Okay. This also happens a lot in mathematics where we want to, we know these will be numbers eventually, but we may not know what they are right now. So we just go ahead and leave them. They look like variables, but treat them as if they were numbers. Okay? All right, let's go through and take the derivative of this. X is our variable. M and n are just like numbers. Okay? All right, so what is the derivative of the top? What's the derivative of x? 1. Okay, the slope of y equals x, the slope is 1. Okay, times the bottom, so we just rewrite the bottom, okay, minus what's the derivative of the bottom? Now again, this is the hard part, but if this was a number, what would be the derivative of a number? 0, okay, so I don't have to worry about it. If this was a number, what would be the derivative of a number times x? It would just be the number, right? If this was a 3x, my derivative would be a 3. If it is a 5x, it would be a 5. So the derivative of the bottom is just n. Okay? Times the top, okay, which just happens to be an x, all divided by the bottom squared. Okay? Now I try to go through and clean up the numerator. And what do we end up with when we clean up the numerator? Just an m, yeah, okay? Because this nx and this negative nx canceled off. Okay, so here is our s prime of x. Here's our derivative function. Now, for part B, find the rate of contraction when the concentration of the drug is 50 milliliters, m is 10, and n is 3. Now it just becomes a matter of plugging these numbers in. Okay? Notice the question, though, says find the rate of contraction. So we're looking for a rate of change, or we're looking for a slope. Okay, so that means we are trying to find the derivative value here. But it's really simple. We just plug in the values that we need, 50, 10, and 3, and we would come up with our answer. Okay, and I can let you do that on your own. All right, so today we've learned how to now work with products and quotients. We have a nice shortcut for finding their derivatives. Okay, we'll see you next time.